Okay. Hi everyone. How's everyone doing? Good. Not much of you are here like after the midterms, right? It's week 5. I understand. Okay. So before I start the discussion, any question in general about DSC30 and like logistic wise and like anything? No. Okay. Yeah, because week 4 we don't have a discussion session, so this week we are going to cover like the linked list and dynamic array with the sorting method. And I know y'all did the PAs on the doubly linked list. So in today's practice problem set, we are going to focus more on the abstract concept about the doubly linked list and what is the difference between like the singly linked list and doubly linked list. And those are considered frequently appear on the exam questions, so pay attention. So oh yeah, by the way, you could download this PDF on the Piazza. I sent emails to everyone with the link. So compared with an array, linked list is a more dynamic data structure that links each data by reference pointer. And let's quickly review the advantage and disadvantage of using a linked list compared with the dynamic array. So the first question, so let's consider those two different data structures. The first one is singly linked list that has 4 nodes, and each node has a next pointer pointing to the next node. And we are not using a dummy node here, so consider the head node and the tail nodes are containing actual data points. And we have a doubly linked list. So what is the differences between deleting the last element of a singly linked list compared with the deleting the last element of the doubly linked list? And what are their time complexities? So my goal is to delete the last element here. What is the time complexity of the singly linked list? O(n). Why? Yes. So for the singly linked list, deleting last is O(n). And what about the doubly linked list? O(1). Why? Yeah, so the doubly linked list only takes O(1) because I have the tail that directly points to the tail, and I know the previous one, right? But why? I also have a tail pointer for the singly linked list. Why is that an O(n)? Yeah. So you need to loop from the head and from each, then go to the next, all the way down to the n-1 elements. So that looping from the head to the previous element of the tail takes O(n). And let's consider this case. So right now, they're the same. Singly linked list, doubly linked list. They're the same. I added a dynamic array. You could just think of it as an array. The word dynamic refers to whenever the element is full, it got double the size. So I can accommodate for a large number of elements. But we're not going to touch on that. So with those two the same data structure, what is the time complexity of deleting an element up front? So right now, I don't want the first element here. What is the time complexity of deleting those nodes? Yes, O(1). Why? Yeah, and how should I do it? How should I delete the first element? What pointer should I change? Yeah, so I cross out this head pointer, so I point to the next thing, right? So in the code, Java does not know what is the next thing. So I believe you have already written some code to test your code in the W linked list, but sometimes it's good for you to write it out, right? So what is the next? So if let's say right now, my head is pointing toward the first node, right? So the next pointer here should be head dot next, correct? And I want to save this head dot next into the head. So it will result in something like head dot next, and like head equals to head dot next. So by the golden rules of the equals, the right hand side got evaluated, and the reference from the right hand side got written to the left hand side. So these lines of code essentially deletes or move this reference pointer from the first node to the second node. Correct? Any question upon this point? So what about doubly linked list? What is the time complexity of deleting the first element of the doubly linked list? Yeah, it's 01. I should say 01. And in order to delete the first element, what should I do? There are how many pointers should I change? Which two? The first one is head. What is the second pointer I need to change? Okay, this one, right? Yeah. Those two pointers need to point somewhere else. So the head pointer should point to the second node, which is as like when we have singular linked list, head dot next equal to head should work, right? Then let's say if I already have this line, head equals to head dot next. How should I delete the second pointer? So it's head. Like that, right? So, okay. If I put the head equals to head dot next first, I have already overwritten the head, right? So you are pointing toward not the second, you are pointing toward the third one. Yeah. So what should be changed? Yeah. So you should do head dot prev equals to null. So the time complexity is 01, right? Yeah. Any questions? Okay, let's see the dynamic array. The number down here is the index of the dynamic array. It's the array. Just ignore the dynamic. It's just the array. So let's say there's some element here. Like let's put a random thing in here. 5, 10, 15, 20, and 25. Let's say I want to delete the first element, number 5. What is the time complexity of deleting the first element? Why? Yeah, correct. So deleting the first element takes about O(n) time. The reason why it takes about O(n) time is array does not allow this empty slot. So you need to copy everything from the index 1, 2, 3, and 4, all the way shifted to left, shifted to left one index. So you need to do, first, remove this index, and second, just take everything from here and move to here. And as you can see, I just select everything and move it to the left. But in programming language, in Java or Python or any language, it cannot do that. So essentially, you're shifting every single element using the for loop. The for loop essentially is, let's say this is a list. It's for int I equals to 1, because we are starting from the first element. And then I smaller than the list length, and I plus plus. So we are just doing shifting, right? LST, the I minus 1 index equals to the I index. And that closed. Yeah. So that takes the linear time. So as you see, right now we have like several data structure that holds like this sequential data. And each data has its strengths and like the drawbacks. And I want you to think about why like deleting the first element of the dynamic array takes such a long time. Why do we need dynamic array? Why do we need like the primitive array? Why don't we just replace anything with doubly linked list? Yes, that's one. Array have index. And what is the advantage of index? Yes. Yes. So because we have a index, that essentially is like a pointer to that specific node, but that is not a reference, but you could calculate the position of the second index. So dynamic array, first, you could have faster access to any element in the array, given that you have the knowledge of which index it is in. So for example, if I want to access the element at index 2 here, I could just, if I have an array, I could just directly point it toward this point, which is 01 in constant time. But if I have a doubly linked list, those dynamic data structure, which is too dynamic, but we don't have a direct access to each individual node, I need to iterate through from the head and like count like okay, right now I'm at index 0. Okay, I step right to the one node. Right now I'm index 1, like that. So array has this instant access to a specific index. The property is pretty good. And the second nice property that we sometimes prefer array is that it's compact. It's efficient because we don't have a sort of nodes in it, because everything is just numbers, right? In the doubly linked list, we create, so remember in your PAs, you create a doubly linked list. There's an inner class, inner protected class, which is called node. And each node has a reference to the prev, to the next, and the data list, if I remember correctly. So that will take a lot of memories. And each pointer is pointing like in another directions or in another random places in the memory. So doubly linked list, and when you have a very, very large data set, for example, you have the genomes, like the AGTC, the DNA sequence of like humans, you don't want to use the doubly linked list because that will take up like the size of the data set will be too large. Yeah, any question upon this point? comparing those two data structures. Okay. So we still have those three data structures. The first is singly linked list, the second is doubly linked list, third is dynamic array. And the question is, we want to searching a specific element on an unsorted sequence. By meaning unsorted here, I means that the data is not in ascending or descending order. It's in a completely random order. So what is the time complexity of sorting an element in singly linked list? So for example, I have 5, 10, 15, 20. I want to find whether 15 is in the singly linked list. What is the time complexity of doing that? What is the best time complexity? What is the best case? Or 1? When is the best case? Yeah. When the element I want to search is the first element, for example, I want to search 5. That is the best case, and it has the time complexity of 1. It's a constant time. What is the worst case? When? When is the worst case? Yeah. If the element is at tails, you will need to traverse the whole list. That's the worst case. So is it the double linked list and array has the same best case and worst case of searching a specific element, if given that the data structure is unsorted? Yes. So the worst case is ON, because you need to traverse the whole list. And the best case is O1 in constant time in the first element. So this is pretty bad, right? Because the worst case, so what is the average case? What is n over 2? What is big O n over 2? Which is also big N, right? Because we don't care about the constants. We just care about how the time complexity. The time complexity only care about how the runtime scales. Yeah. So the average complexity is still big O of n, which is pretty bad. Because what if I want to do? What if I really want to do a lot of memory query? What if I want to do a lot of those lookup? So one strategy of speeding up this lookup process is sort the sequence, right? That's what we are learning right now. So we just finished the singly linked list and doubly linked list part, and we headed toward the sorting sequence. So then let's think about, what about searching a specific element in a sorted sequence? Let me put some numbers in here. Okay, let's say I want to find 15 in a singly linked list. What is the time complexity of doing so? Or a random element? Right now the data is sorted. I know the last example is still sorted, but right now I can tell you that, okay, my list is sorted. What is the time complexity of searching a specific element? Why? Yeah. So it's still ON because the nature of the linked list forces you to start from the head. And I search the first element, the second element, the third element. Okay, bingo. I found it here. So the way that, okay, I need to find the first element, second element, and third element. I cannot skip anything, right? So right now it's still N, which is still pretty bad. The time complexity of linear time is not bad, but it's not the best. So we want to optimize that. What about doubly linked list? Does adding an additional pointer of previous pointer help? Yes or no? Raise your hand if you think it does help. It's the same, right? Because you still need to iterate through every single node to see, okay, whether is this the element I wanted. What about dynamic array? Let's say I have 1, 3, 5, 7, 8. What about if I want to find whether 7 is in this array? What is the time complexity to find the element 7? I don't know whether 7 is in which index. What is the time complexity of finding the 7? ON? How? Yeah. So one approach. So the approach you're suggesting is called the brute force search. Which means that we just check each element, right? From the first index, second index, or the index 0 all the way to the n. But isn't that what we did when the sequence is unsorted? When the sequence is unsorted, we still do this like brute force search, right? We search the first element, the second element. So, which means that we didn't improve our ability to have a faster or a more efficient way to search a specific index or element. Which means that the sorted sequence, the sorted information is being lost. Is there a way that we could use this information as under the premises that, okay, this array is sorted? Yeah. A binary what? Yeah, binary search. Yeah. The second approach is called binary search. So I'm not sure whether the professor covered in the class. I haven't been to the class, to be honest. And it's been a while. It's been like 2 years. But the strategy of binary search actually use the information, like leverage the premises we promised ourselves, like, okay, this sequence is sorted. So the strategy of the binary search is, let me finish. Okay, instead of looking the first element, I started looking the middle element. So I started looking the 8. And then I asked myself, is 8 larger or smaller than the target I want to search? Is 8 larger than 7 or smaller than 7? So because 7 is smaller than 8, right? So because everything below or after the index 4 is definitely larger than the number 8, right? So I could just ignore those. I could just strike those out and don't even look at those. And then the second element I want to look up is still the middle element, 5 or 3, whatever. And then I asked myself, is 7 larger than 5? The answer is yes. So because all the element on the left-hand side of the 5 is smaller than 5, so I could ignore those. So right now I'm right here. And I ask myself, is 7 equals to 7? The answer is yes. So I found the element. So this strategy is called binary search. It essentially allows us to discard a lot of information that we don't want to even see. So that is one benefit that we could use on the premises that if the sequence is sorted. Any questions? I have a question. Can we do binary search on doubly linked list? Why? We don't know the... What if I have the n element, which is the length of the list? Yeah. So we don't have a direct access to the middle index. So that's the exact problem we have. And that's why when you are actually sorting something in later PAs, we usually sort it in an array, not in a dynamic data structure. Yeah, any questions? Okay. So right now we come to the practice number 2, the sorting algorithm trivia. So the sorting algorithm is the one major topic that you are learning this week. And sorting is essential to keep your data or things, belongings, organized. And the purpose of the sorting, I want you to really think about this. The purpose of the sorting is to enable the faster query on this organized sequence, right? So we spend some time, organize our data in a random sequence and make it into a sorted sequence. And that allows us to have this nice, sweet property that we could look something up pretty quick in a logarithmic time instead of a linear time. So for the details of like the sorting, the implementations wise, I have a link here that really like visualize step by step, like Zybook, but I think this one is better. So here, they have a lot of sorting algorithms that you to choose. And like the quicksort, let's start with quicksort, and if you click run, it generates like a sequence of data in a bar chart or histogram, whatever. And then you see there's a number of steps, like 80 steps in total. So if you click right, it actually shows the step, like select the pivot. So for this question, the quicksort is selecting the middle index at the pivot. And then to move the pivot to the end. Yeah. I just wanted to quickly demo how powerful this website is, and feel free to play around with it when you're like either doing homework or you're like confused about how different sorting algorithms work. Definitely use that. And I really like this picture. It's a big old complexity chart. So sometimes it might be confusing, right? What is the meaning of O n squared? What is the meaning of log O n? What is n log n? So this graph actually shows you the rank. So the worst is the n factorial here. Okay, a quick quiz. What sorting algorithm is in n factorial? Selection. The selection has the I think worst case is the n square. So n factorial is like really, really bad. We don't want to have something like that. So the one sort in n factorial is we call Bogle sort, a monkey sort. It has a funny name. Like if you have a deck of cards, if you're like a monkey, just throw them in the air, and then you check. Okay, is it sorted now? No, I throw it again. So if randomness, if like throwing random for a lot of times, it's unbounded. So it's like exploding real quick. Yeah, that's a side note. But to pay attention to like the different ranking of the time complexity, you see that ON's here. So linear time is pretty good, right? Compare with the n log n squared, and the exponential time. But the even better one is the log n and the constant time. So when you're designing your algorithm or thinking about questions, so really you should really think about how you could aim at those two time complexities. Okay, I love this question. I just came out like 2 hours ago. So I was at Geisel at A4, and okay, what should I do in the discussion? Right now, imagine you are at Geisel library. You are presented with n unsorted book. Your goal is to sort them by their titles according to alphabetical order. That's a sorting question, right? I have a sequence of unsorted element, which is, in this case, is the book. Which sorting algorithm should you use to minimize the sorting time complexities? Or in general, the time? Okay, I have two scenarios. The first is the n is extra large, like 1 million. And you cannot sort it by yourself. You sort a book for 2 hours, and you ask your coworker to replace you in sorting the book. You won't tell your coworker your current progress, since you want them to suffer another 2 hours. Okay, take about 1 minute to think about which sorting algorithm you should use. And just a reminder, we have those, whatever sorting algorithm we have. You can ignore the one we didn't cover yet, but yeah. Think about 1 minute. The best one. The one to confuse others is just the fact that you don't want to tell your progress. Yeah. You could talk to your peers, neighbors, if you want. Okay, any ideas? You could just shout it out, you don't have to explain why. Okay, which one? Selection, insertion. Any other thoughts? So we all agree we should use one of this or both of them, right? Any objection to those two approach? So insertion will be a little bit better, so let's think about if we want to do selection. Let's be evil here, right? Let's start at evil here. Let's think about selection first. So the procedure of selection sort, the name of selection means that I select one by one, right? I select the largest one and select the second largest one. I select the largest one and I continue to select the next extreme value, right? So what will happen if I use selection sort? After I sort, okay, let's say I have 1,000 books, and then in 2 hours I sorted 100 books, which is pretty quick, like a minute. If you think about it, if I sort like 100 books in 2 hours, that means that I need to find the largest book. I start with Z, like 1,000 books in a minute, which is pretty amazing, right? It's hard. It's a hard task. After you finish sorting 100 books, there are still 900 books that need to be sorted. But you are evil. You don't want to tell your you don't want to tell your coworker your progress. So like you put everything back, even though you're sorted. What will happen if you use selection sort when the coworker comes? They will start at the largest value, right? They will start to looking, okay, where is the first largest value? Where is the second largest value? So you are doing repetitive job. And so in the reality, because you are finding it in among like 1,000 books, right? So I will argue that your coworker will see, okay, here's the largest one, and here's the second largest one. So you don't have to shift it. So in selection sort, so because our humans are like pretty good at recognizing the patterns, right? We recognize, okay, all the books starting from Z already sorted here. So you don't have to specifically looking for, okay, is this sorted? But one thing your coworker is confused about will be, is it in sorted order? Right? It's nearly sorted, but is it sorted? So they need to check it, right? They need to check it. The time complexity of checking whether it's sorted also takes like a linear time. So what about insertion sort? So insertion sort is I pick up the largest value and I insert it somewhere, right? Wait, what is insertion sort again? Yeah. Yeah, correct. So the sorted part, the partially sorted part will remain the same when you go to your other coworkers. Even though you don't tell your progress, the bookshelf tells the progress, right? Actually, I want to polish the question a little bit. You won't tell your coworker your current progress, but you will tell them which sort you're using, right? Okay. Any question for the first scenario? Okay. Then the second scenario is the area is relatively small, and you are in a huge spacious room, and you can move and stack books easily. The example of N right now could be like 200 books, not a lot. Which sorting algorithm you want to use? And pay attention that I mentioned that, okay, you're in a huge spacious room, and you have a lot of room to operate with. And yeah, take about 1 minute, talk to your neighbors, and like think about which sorting algorithm you like to use. All right, any ideas? Like, which one should I use? Yeah. Why? How is the fact that I have a lot of rooms helps the merge sort? Yeah, correct. So that's a powerful idea. Is given that you have a lot of space, you could. So in practice, how would you like to do that? Like, I give you a stack of books. How would you like to use merge sort to sort it? Yeah. So I have a question for you. So what is the base case of the merge sort? Okay. So the point I want to make is in practice, in like when we're writing programs, we're splitting it half by half, right? For example, I have those are my books, and I'm splitting it by half right now. Right, split into two halves. But the base case, you are splitting it all the way down to when you have a single book, right? Like a lot of them. So in practice, you could just put one book here, each book individually, and start to directly merge them. Because you don't have to manually split them half and half, because it's time consuming, because you could just place, okay, one book here, all the way to 200 books right on the back. Any questions? Okay, how? You could use any sort, right? But the question is quick sort efficient? And is it? It takes the same space, I think. Wait. You mean space complexity? Yeah, I think quick sort does not take that amount of space, but is it easy to operate though? Yeah, both merge sort and quick sort is in log n best case. Yeah. So the reason I didn't a little object with the quick sort is the quick sort you're picking a pivot, right? And you're doing comparison from here all to the end, which is a pretty hard job when you are a human. So the number of comparison is relatively large for a quick sort than the merge sort. Yeah. Any questions? Okay, the last point, some philosophy. Is that the fact that the linear time is always like a lot worse than the logarithmic time? Or in log n? Is it, after all this, is it in our daily life we should sort every single stuff? We should sort our clothes according to the color? And we should sort everything for the faster access? Is that true? Yeah. So the point I wanted to make here is to think about the operation of sorting. You are paying some time and energy upfront to make your thing organized. For example, in the book example, we are paying a lot of times to make book fastly accessible for other student, other reader to access it, right? But is that, so I believe for the Geiso library, you have to sort it. Otherwise, everyone cannot spend like linear time to search every single book to get one book they want, right? But in practice, a lot of questions does not need to be sorted, because sometimes the sorting time takes longer than access time. Just take an example, like whenever you do your laundries, you have a lot of pairs of socks. You sort them, like at least I sort them every single time because I want them to easily accessible, right? But sometimes I ask myself, do I really have to sort it? And I just pick random pairs up, and then I just take it. So sometimes it's you need to weigh the benefits, the cost and the benefit you are getting from the sorting. Because sorting is actually an investment in the futures for the future easiness of getting access of something. But if you know some cases that, okay, I have a lot of things, but I only need one thing in the future, maybe it's wisely to just brute force search. You don't have to sort anything. Sort everything. Yeah. Okay, that's it. That's all I have for today's discussion. So if you have any questions, feel free to come here and ask.